Is this visible?
Yes, sir.
Shall we wait for others or start?
Sir, wait 1-2 minutes, then start.
Okay. Okay. Okay.
Good evening, sir.
Good evening. Welcome all of you. Last day I have discussed about the some characteristics, the intrinsic characteristics of MEMS, and I have uploaded the lectures, videos, and one extra video I have uploaded. Have you went through that screen, that video, all of you? Have you seen it? Have you seen that video? The microscopic devices.
Yes, sir.
So all of you again have some knowledge, basic knowledge about the uh, MEMS devices, how they looks like, how they operates or creates. I think basic idea has been already grown.
Yes, sir.
So today I'd like to discuss about the MEMS fabrication steps. Okay. MEMS and IC fabrication cycle. Here is a chart. So it starts from here is the design thing, and bottom of the cycle is the fabrication cycle. Okay, which is executed in fab lab, fabrication lab. So first you have to design a particular MEMS device, and what are the steps? First you make the solid models of the device, uh, and that solid model means you are going to use a certain material, maybe that is the crystalline material, or that may be amorphous or some other materials, ceramic materials also maybe. So that material you first model it, and free from the geometry. That means the that particular material may not be a regular geometry or regular shape. It may be irregular shape. Okay. So in irregular shape, body or material, simulation is a little bit difficult, and only the numerical you have to use the numerical tool is the only technique by which we can simulate any kind of the irregular shape or free shape body. Okay, so simulation, we need different simulation softwares are available through which we can shape the body. So that modeling is to be done first. That is called the modeling. Okay, simulation modeling. Then we have to couple many other property because in MEMS involves the electrical, mechanical, fluidic properties also. Okay, so different properties can be incorporated into the design. So first is the concept of a new device, specification of process. So then you have to use certain simulators, and using that simulator you couple the electrical, mechanical, fluidic or kinematic properties also. You include that. Then with that, this the 3D solid model, basically the finite element model, you have to mesh it, and you have to define the size of the mesh. Okay, so this mesh term is related to that simulation. Okay, simulator based term. Then you couple these properties with that particular solid body. Then you simulate it, and when you are satisfied with the simulation result, the next is the making of the layout. Making of the layout. Now, after making the layout of the device, MEMS devices, then you have to go for mask making, and that is generation of physical mask or direct write pattern, which is performed in this case here. So a direct write pattern, sometimes we use it for making the master mask, and then we get step and repeat uh, the using the camera, and using that we get the regular mask which is used for fabrication. Okay. So now once the mask is fabricated, then design part is over. So here is total design part is over. Then you come to the fabrication lab or fab lab, and there it starts from the substrate. Okay, starts from the substrate, crystal substrate, and that is the blank substrate. uh, so it is basically first step. Uh, we have the material. In case of silicon, suppose silicon, the single crystal silicon is used. A single crystal silicon is used. So I will show you maybe 1-2 slides after that how this single crystal uh, silicon is grown and polished. And then here in case of MEMS technology, the mainly we require the deposition of material. After that, patterning of the material and removal of the material. Okay, first deposition of material, then patterning, then removal extra materials. So this process, this cycle is continued. Okay, so deposition, then pattern, then removal. This cycle is continued. So here on the wafer you deposit certain material. So these are these are blank wafers. We deposited certain material on the wafer, and then we have to transfer certain pattern. Then the pattern, this is known as pattern transfer, this one. And then the removal of material, or uh, this is called the lithography process here in this case. So using the lithography technique, the pattern is transferred, and you can see here, this is the film here on the wafer, and here some pattern has been transferred. And after transferring the pattern on the wafer, then selectively you have to remove some of the materials. Okay. some of the materials. Removal of selective of the material, and that is basically the etching, which is called etching, to remove of the extra material. Okay, those are not used for certain operation. That is the extra thing can be removed. That is called the etching process or machining process, and it is related to micro structure. It's called micro machining. Okay, so we will discuss about these techniques later on. So removal of so etching and machining. After it, then wafers look like this. Okay, so this cycle may continue. This cycle may continue. So maybe once, twice, or thrice, or repeatedly, depending on how complex is your process. So how complex is your device structure? Depending on that, this cycle will continue, uh, and after that we will come up with the wafer having different kinds of structure and different kind of sensing or pickup electronic circuit on the structure. Okay, one small circuit is to be incorporated into that structure. So then next job is the probe testing. After using the probe art machine, we have to test it. Now bounding before bounding, uh, testing is done by using with the help of certain probes. So probe testing is being done, and whenever you are satisfied with the probe testing, then you have to do the sectioning, means cutting process. Okay, sectioning. So sectioning means small pieces you are getting from the whole wafer. So small pieces, this is the whole wafer. After sectioning this, we can got this. And it's called individual die. Okay, so individual die is put on the package base. So how many package bases you take the connection, that is the varying from the bond pads to the external leads. So that connection is known as assembling to the package. And after the bonding is over, then we have to seal the package. It looks like IC, one type of IC. It seal the package. The package sealing is being done. After sealing the package, then we have to go for a final test. So here we're doing one test which is known as the probe test, and here the final test. So number of devices which you are getting here, which shows the correct results, that number may reduce here because of the intermediate certain process steps. But here some special points are to be mentioned, because from here, in case of IC packaging and testing, the loss is less, very less. But in case of MEMS devices, that is the difference between IC packaging and MEMS device packaging. So damage is more. In MEMS devices, damage is more, because in MEMS you are going to use very thin membrane or thin cantilever or a thin structure. So special probing, sectioning and handling procedures is to be adopted to protect a release part. So some of the structure, a roof mass is hanged to the help of a cantilever. If you have seen the cantilever beam, you can easily figure it out. So if you go for conventional probing and conventional packaging, which is used for VLSI packaging, very large scale integration, VLSI packaging, so that will not solve your purpose. So you have to go for special technique. Okay, so VLSI technique is not actually incorporated into MEMS. So what is the special technique? Why you need this special technique? Because if you don't have that special technique, a lot of the structure will be released. Okay, that means which are hanging in case of MEMS devices, they may break and you can spoil the devices. So there is still some part, another distinction from the normal ways. I think that you have to seal some selective parts. So in case of VLSI, the complete part is sealed. In VLSI technology, the complete of the full device is sealed and packaged, and the external leads you can connect by wire using some external wire, or in PCB board you can put it. But in MEMS packaging, some portions you are covering and some portion you should not cover, because that will be in touch with the external world, physical world. For example, assume in case of gas sensor, the sensing element must expose to the environment, that you cannot keep it inside the packet, okay, inside the package system. Similarly, things are not there in case of VLSI. The whole complete thing you can seal. Okay, so in MEMS, some portion which requires the interaction with the environmental world has to be taken outside the sealed portion. So that this is the difference in the normal VLSI package and the MEMS package. So then you have to final test and something in a test. If it qualifies, then you can go for the marketing. Okay. So, so this slide shows the conventional methods, conventional process or steps taken from the VLSI technology steps. Those are crystal growth, thin film deposition process, pattern transfer lithography, etching of materials, doping semiconductors, metallization, then bonding and packaging. Okay, so all these VLSI steps are also used in MEMS. So this has been taken from normal IC technology step. So first, let one by one we will discuss. First, let me discuss about the crystal growth. Starts from. So crystal growth, basically silicon wafer fabrication. Silicon wafer fabrication. You can see here, this is known as Shoklasky technique. Okay. If you have pen and paper with you, you can note it down. The technique is called, this technique is called Shoklasky technique. CZOCHRALSKI. Okay, Shoklasky technique. So here silicon is melt, and here is the quartz crucible, and these are the heaters. So it has melted nearly 1400 degrees centigrade. 1400 degrees centigrade. Okay, there is a seed crystal. So then this is a seed crystal. When you pull the crystal, just you rotate it and pull upward. So automatically from the seed, the crystal will fall, and the orientation of the crystal, where it is 100 or 111 or 110, all things depends on the seed crystal. Okay, so if you take 100 seed crystal, 100, 100 means 100 seed crystal. So crystal sizes are defined in this way: 100 is 100, 111, 110. In this way, the crystal sizes are there. So this 100 seed crystal, the crystal will form according to that orientation. So after pulling, that means very slow pulling and rotating, and rotations is being given so that you can get uniform diameter, the ingot. Okay, this one, this is called ingot, ingot, ingot. That thing is known as ingot. So this bottom figure, just after pulling you got this ingot, and if you cool it, cooling is so also important in this case. So when you are cooling the melt, so automatically the impurity, which are lot of impurities may be there in the melt, which is not dissolved. So those impurities atoms, and this by segregation 8 will come into the hottest zone. From the cold zone. Okay, as a result of which, if you slowly cool down, so from the cool zone it comes to the hotter zone, and at the end of the process, those particular end few slices you can reject it, so that the other portion will be pure. You will get the pure crystal. So after getting after getting that, your next, there is the industrial house where a lot of these crystal coolers are there. Okay, so after getting this ingot, next step will be to make slices. Okay, so cut into different slices. This one, from this position, it will be cut it from this position, then this, so round shape cutting will be there. This is called slicing. Okay, so these are the instruments which are used for slicing. The ingot is placed here in this position. So the diamond cutter is there. So you see, by slicing, the ingot is made into thin slices. This one, thin slices. After making thin slices, it is basically transported here. Okay, so which is basically the polishing machine. So they are using certain fine green powders, and maybe some fine green carbon particles also is used for polishing, along with some fluid, and just using 3-4 wafers. So these 3-4 wafers, and certain rotation was uh, giving using certain carbonate on its powder form, small particle carbon. The diamond particle is another helping in the cleaning or polishing these materials. Okay, you can use those to get the polished single crystal silicon. Single crystal silicon. Okay, now after getting the this wafer, silicon wafer, you can process the wafer. So the next step is the thin film deposition. So thin film deposition, one technique which is known as the spin casting or spin coating technique. Okay, some book defines this one is the spin casting. Some consider it as spin coating. Okay, or the different research papers also are mentioned in this way. Okay, so both are same, spin casting or spin coating. So spin casting technique which is used here, uh, this particular technique will not give you very good quality of the crystal, even then. So this is used in some cases where normal deposition facility is not available. So here you see that using this nozzle, it's a nozzle, you just eject some of the liquids here. You see through the nozzle, and then this particular chuck, this is called chuck. So this chuck is rotated at high speed, so that using the centrifugal force it will spread over the wafer, the solvent will spread, and at the same time what in that particular paste, what the solvent that will evaporate. Okay, just evaporate. A total mixture will spread, and solvent will evaporate, and as a result of which at the end you will get the film, casted film only. Okay, there is some here evaporation is there, then spin off. Okay, so it is in this way. So there is some sort of spinner arrangement which is used for thick film. A photoresist coating, similar kind of thing is used here. So here one thing is the material must be in a liquid form, otherwise you cannot spread over the entire slice. Okay. So this is the slice, it will be spread over the slice after evaporating. So now this particular thing has certain problem, and this type of film have a high stress value. It will have less dense and more susceptible to chemical attack. Why? The reason is that when are you spreading the film over the chuck, by rotating chuck you are putting the liquid, then at the same time evaporation takes place. Now during the evaporation of the solvents, so it leaves some pores. Because of those pores, the film will not be highly dense, and at the same time when you subsequently use those films through the pores, some other gases may enter, and that is why it is susceptible to chemical attack. Because of it is less dense. So that is why this particular technique is not that much popular technique, although it is used in some typical cases. And here is the actual system. The spin coating is shown in this diagram. Now this is one technique, and another technique is the evaporation technique. So this is thin film deposition technique. One technique is called the spin casting. Okay, another technique is evaporation technique. So they basically there are certain basic principle. What is the working principle? We load, this is the principle of a simple evaporator. What happened? Okay, if this meeting is ended by I have only 7 minutes. If it is ended, then all of you must join again. using the same link to continue the second session. Okay. Okay, so a simple evaporator, how it works, the working principle based on these points. Now we load certain wafers into high vacuum chambers, which are commonly pumped with either diffusion pump or a cryo pump. So now, why we need this vacuum chamber? Why? Because vacuum chamber is required to reduce the contamination from the environment. Okay. So different contamination may be happened with the wafer. So to remove this contamination, we need to uh, vacuum the chamber. At the same time, if you evaporate any material in vacuum, its melting point and evaporation temperature will be less. So these are the two results why we need vacuum for evaporation of certain material. So now if we use vacuum chamber, then we have to use certain vacuum pumps, and we used to and there are two types of pumps basically. One is the oil pump, other is the oil free pump. So in earlier days we used to depend only and on oil pump, that is rotary pump actually, or it's called the diffusion pump or turbomolecular pump. Different, it has different names. Okay. But nowadays a separate class of pumps that is available in the market, which you can use, and there will not be any contamination from the oil. Okay. All of you know that oil is a source of hydrocarbon contamination. So now if you use pumps which uses oil, so there is a chance of some contamination of hydrocarbon into the vacuum chamber or into the thin film, the wafer thin film. So nowadays most of the vacuum chambers in VLSI lab, they use oil free pumps. They are namely the cryo pump or the molecular iron pump, or sometimes it is called the sublimation pump. The cryo pump, they use liquid cryogenic material, basically liquid nitrogen. Liquid nitrogen. Now liquid nitrogen actually basically condense most of the gas molecules which can condense near temperature of the liquid nitrogen. So those will be condensed and that will be observed by certain materials, so automatically vacuum will be created. So you know, in an atmosphere the major portion is nitrogen. So you can liquid nitrogen and oxygen will just means these two constituents, like nitrogen and oxygen, are liquefied, then automatically in atmosphere most of the gases are gone. So pressure will go down. So that is the basic principle of the cryo pump. After then you can use the cryo pump. You can use the sublimation pump also for very high vacuum level. If you need to vacuum level makes it high enough, you can use the sublimation pump also. It's another high performance pump. So now in this evaporator, one should be the one vacuum chamber is used, which is evacuated by certain pumps. Then what is the next thing you need? The next thing you need a crucible. Okay, crucible, and on which you put the material, and by applying certain power, electrical power, you can evaporate those materials. So crucible actually it holds the material, is film. Okay. So actually in crucible materials are put so materials are put into this crucible, and it is electrically supplied, power is given, and you melt inside the crucible. The material will be inside the after melting this uh, material will be evaporated and it will be deposited on the wafer. Okay, so what I need to deposit the material over this wafer, silicon wafer, I need to put it inside the crucible. Okay, then melt it. So that is the basic principle. You need a vacuum chamber, you create the vacuum, you put the material on inside that crucible and evaporate it. Then you apply certain electrical power into the crucible, and crucible becomes hot, and when the temperature exceeds the melting point of this particular material, so material will evaporate. So that is the basic working principle. Okay, so basic principle of evaporator. Now you can see here a schematic diagram of that evaporator. This is a vacuum chamber, and on the vacuum chamber this is a diffusion pump. It is connected over here, and using this diffusion pump you can replace the diffusion pump by as I mentioned, that cryo pump also, or other sophisticated oil free pump, and the required vacuum is of the order of 10 to the power minus 10 to the power minus 6 to torr to 6 to 10 to the power minus 7 torr. Okay, so 10 to the power minus 6 to 10 to the power minus 7 millimeter of mercury, and you have to